this is an extended talk of my SciTech talk I did 3 weeks ago. And comparing two approaches for second and third order schemes. And this is a paper co-authored by Jeff White, the developer of NASA Falcon CFD code. And this work has been funded by NASA Hypersonic Technology Project. Okay, so I'd like to begin with this interesting experiment conducted by a neuroscientist. So neuroscientists said humans are hardwired to pick the easiest path. This is a very interesting, very simple experiment. So you look at, there's a screen. Dots are moving to the left or right, okay? And then there are two handles, left and right. So if the dots moving to the left and you push the left handle, and if you see dots moving to the right, you push right handle. It's pretty easy, straightforward. But something interesting happens when the scientists gradually add some weights to the left handle. So left handle gets heavier, but you don't notice it is so small. But then the people tend to more likely to push the right handle, even though you see dots moving to the left. And this is, I read this paper and it's amazing. And you don't realize it, you're just doing it. So that's why they say humans are hardwired to pick the easiest path. So the cost of actions can influence perceptual decisions. It's amazing. And the same thing can happen in CFD algorithm research. That's the story I'm going to tell. Well, yeah, just a little bit of weight, and you don't notice it, and you push the right handle. Amazing. Okay, so I've been working on this economical third-order cell-centered finite volume method for text and the mixed elements. And economical means the third-order accuracy at nearly the same cost of second-order method or unstructured gradient towards high-fidelity hypersonic flow simulations. And I've been pursuing basically two paths. One is on the left, this is a node-centered third-order scheme, third-order H-based scheme based on hyperbolic analysis tools with an adaptive mesh. And also on the right, this is a cell-centered economical third-order scheme. And there's a common interest here is the economical third-order methods with a single numerical flux per phase or edge, and not requiring second derivatives at all, and which usually required for third-order accuracy towards automated CFD with the fully adaptive tetrahedral grids. And this talk will focus on cell-centered version. But let me go back to the origin of this work. I started to work with Jeff White on the NASA Falcon CFD code, developing a second-order finite volume scheme. And this is the usual second-order finite volume for invested discretization. You have solutions at cell centers, and you need to linearly reconstruct solution to the phase center and then compute numerical flux. What you need are the gradients at cell, right? And of course, usually conventionally, you compute gradients by least squared using the values from the nearby cells, and then do the linear reconstruction. But we follow this interesting work by Fan Zhang to instead compute and store gradients at nodes rather than cells. And you average the nodal gradients to get the cell average. And this is the original approach proposed by Fan Zhang. And then we discovered there's another way. We can do instead of cell average, we can do phase average. So instead of averaging these 4 gradients, we average only the 3 gradients over the face, triangular face. And this way you can achieve third-order accuracy, and also you can reduce the stencil size. There are some advantages. But overall, storing gradients at nodes has advantage because the number of nodes is much less than the number of cells. You save a lot by computing and storing gradients. And then we move to third-order scheme. And still we keep gradients at nodes. But as you can see here, here's a baseline second-order method, and we just add correction terms to the flux and the source term. And then you achieve third-order accuracy, and still with a single numerical flux per phase, and no second derivatives required. And this is amazing quadratic interpolation scheme. This looks like a second linear reconstruction, but this is actually exact for quadratic functions. And this grad WT is the average over the face, 1, 1, 2, 3, and then WJ, this is a average over the cell. So this is actually the average of the CA energy and FA energy that we developed previously. And the flux correction, we only need gradients at nose, and then source correction, we need only the gradients at nose of the source time. So this special scheme was derived for tetrahedral grids originally, but many current practical CFD simulations are still performed with mixed elements. So it would be great if it could be extended to mixed element grids. So hexa and the prism and the pyramids. So that's what we started this work. And so we have to extend these algorithms to beyond tetrahedral meshes. But the most important part of this extension is the efficient quadratic interpolation scheme. Does this extend to non-tetrahedral cells? This was a big question because this was derived for tetrahedral cell. Let me show you. So I started with this interesting formula here. This is a projected derivative of the gradient. Okay. And this gradient is evaluated with the Green-Gauss gradient over the cell because we have gradients at nose. And then you can do some simple algebra, and then you figure out that this is actually the phase average gradient over this phase minus the cell average gradient. So it can be written in this form. So second derivative term can be expressed only in terms of gradients at nose. And using this identity, you can write this quadratic interpolation. Here is the curvature term. You can replace this red part by the difference between the cell average and the phase average. And then you can combine this linear term and this curvature term, and then you end up with this second derivative free quadratic interpolation scheme. And as you can see, that this is actually the average of phase average and cell average linear reconstructions. And this was a big discovery, and it was so easy to implement because we already had phase average and cell average for second order schemes. So now can we extend it to other cell types, right? It relies on this Green-Gauss over TET. But if you look at this Green-Gauss is exact for linear functions over TETs, but not for non-irregular hexa or non-tetrahedral cell. So there was no, at first it was not possible. But looking at this different way, you actually find this is possible. So forget about cells. Let's look at this projected gradient. Okay, so here's a linear function. And then this projected gradient is just a difference between this ux here and the minus uj, right? So if the u is linear, this is exact because it's just a linear function. And then if you substitute the u, some gradient of some quantity into this formula u, then you end up with this interesting formula, right? So this is exact linear gradients or linear quadratic functions. So actually, you don't need a Green-Gauss gradient, and this works for any cell. And in a cell, you need a way to get the gradient, the point where you want this to use this formula. So for TETs, we wanted to have this gradient at the phase center, and it happens to be the phase average is the linear interpolation. So we need to find this interpolation for a non-tetrahedral cell. And then this was also easy. And we can apply this formula to any point, but if the phase center is defined by an arithmetic average of the nodal coordinates, and then we can just average the gradient, nodal gradient, and this is exact for linear functions. And same for the cell average. And so we can use this form exactly in the same way, as long as we linearly interpolate the gradient and at the phase center and the cell center. And using arithmetic averages to get the coordinates, you can use the arithmetic average. You can move this point around, then you will need more general linear interpolation coefficients. Okay, so this can be extended, and still we don't need second derivatives. And the rest is actually easy if you split all faces into triangles. Because once you split all quads into triangles, this is a polyhedral, and clearly defined. And you can compute the volume, and you can do the volume integration. And the flux integral, you can apply the tetrahedral scheme to each triangular face. So the rest is easy. And so I took this approach and then presented this paper in 2024. I think it was cited. But it requires 2 numerical flux computations per quad face because I split this into 2 triangles. So can we reduce the cost by developing a single numerical flux approach? And yes, answer is yes. And it's already done. Okay, let me go back to second order accuracy because for quads, you even lose second order accuracy unless you do something special. Okay, 2 approaches to guarantee second order accuracy. One is a split face. This was demonstrated by Katz and Sankar in 2011. It's relatively simple. You split a quad into 2 faces and then do the numerical fluxes. Okay, and then you can do third order tetrahedral scheme, and that's what I did in 2024. And the flux correction approach is an interesting approach. I was inspired by this approach developed by Brenner in 2010. And then I was able to derive some correction term to the numerical flux to achieve second order accuracy for non-planar quad face. Basically, you split the face into 2 triangles or 4 triangles, and then you exactly integrate the polynomial. I will show this next slide. And this is economical because you only need 1 numerical flux. But this was a bit more complicated to implement. And how it is derived for second order accuracy. Okay, so here's a linear flux, linear polynomial of the flux. And I just need to integrate this exactly over this quad. To do this, I split quad into 4 triangles. It can be 2. And then for each triangle, I can integrate this linear polynomial exactly. And so that's why I have a summation over the 4 triangles. And then I can arrange the result in terms of a numerical flux at the center, and then the correction term. And this correction term is a double dot product of the flux gradient and this tensor. It's a matrix, geometric matrix defined by this. This is the sum over 4 triangles. And but this matrix is called correction matrix, and you can compute it for given mesh and keep it. And then you only need, when you use the chain rule to compute the flux derivative, you only need the gradient of the solution. And this technique has been implemented in NASA Vulkan CFD code to achieve second order accuracy on any grids. And then recently applied, this technique has been implemented in a node center scheme in SU2 by Tommaso Velosta and Luca Albergo at the University of Milano in Italy. And also cell center finite volume in SC flow, cradle hexagon, the commercial CFD code. Now, to do third order, we need to add quadratic term and integrate this exactly. And still, the result is relatively simple. For each triangle, I integrate this quadratic polynomial and the linear polynomial exactly. And then I can use this interesting identity to eliminate second derivatives. Second derivatives in terms of nodal gradients. And then I end up with this correction term for third order accuracy. So this term is the same as the second order correction. And the second term is the extra term required for third order accuracy. And I derived it in June 2023, long time ago. But I didn't implement it. And I tried the split face approach. And why? I think easier path. I was lazy. Of course, I didn't realize it. But split face was intuitively easier to implement. And it works, and it produced third order accuracy. So do I have to, anything else? But the flux correction approach has, of course, advantages. Economical with only a single numerical flux. This is really good. Also, it's less biased with 4 triangles. than two triangles split. In a parallel environment, yeah, at the partition boundary, you need to figure out which split you're using from either side. But the four triangles, there's no need. And you don't want to do four triangles in a split approach because then you need a four numerical classes per face. So there are advantages, and the discussions with colleagues and comments from audiences, and it helped me correct my perception. So I submitted an abstract to Scitech 2025 and promising that I would present third-order scheme with flux correction. At that time, I still didn't implement it, but I already derived formula. And in August 2024 abstract was accepted. I thanked the reviewer for giving me a chance. So I started to implement it in my code. And if you try to do it, it's not really difficult. The implementation was relatively simple. And we can implement this correction term in terms of some flux Jacobian projected in various directions, like a column space, ABC, and then these gradients, the flux is normal to the triangular face. So it wasn't very difficult. It took only a day or two to implement it. Okay. And the volume integrations are simple with quad split into four triangles. So I had this single numerical flux plus correction, again, without second derivatives. And the volume integration and the volume integration of source terms, they can be integrated precisely because now we have, this is a two split, but we have four split also. So when you split the quad, the volume is clearly defined and you can integrate it. So again, second derivative free, third order algorithm for mixed element grids. So we have a set of schemes to compare. The baseline is second order, but not exactly second order on the irregular mixed element grids. The volume is ambiguous, and but the flux is 1 point. It's cheap. And then split face schemes, baseline plus split two, you split the equal face into two. This is the second order scheme. And then you can add correction term from the tetrahedral scheme, and then you achieve third order accuracy. And this was presented in AIAA Aviation 2024. And the flux correction, second order, I split into 4 or 2 and add a correction term. And this is a second order scheme. We have now the third order scheme, which has a different additional correction term. So this was the scheme presented at Scitech 3 weeks ago. Okay, so my code, yes.
So this is per face, so it doesn't, you could have a pyramid, right?
Yeah.
It's not all sides have to be 4 or 3 points, or it all have to be triangles.
Oh, you mean polygon? Polygonal
face.
Yeah. You split any polygonal face into triangles, and
the split point is always just defined as the arithmetic center of.
Yes, that's right, exactly. So I only implemented this in my test code, and it works on hexa, prism. I don't have pyramid, but and then this is a serial code, so these test cases are small size, but. We solved the Euler equations over 5 levels of irregular hex mesh and measure the solution error in the x velocity. This is a contour of the x velocity and with using manufactured solution. And so now look at this error known for the velocity versus the mesh size, effective mesh size. The baseline scheme, it loses second order accuracy as expected. This is first order slope. So it's first order, and this is expected. And then the second order schemes are these red the symbols. Baseline face flux correction 2 split, the flux correction with 4 split, or baseline with split 2. All give almost the same second order results. And third order split 2 or face flux correction, they give third order accuracy and no differences. But the point is that the cost. When we look at the iterative convergence, the residual versus iteration, there's not much difference. Third order scheme, it takes, I don't know, maybe 5 or 6 extra iterations to get to bring the residual 8 orders magnitude here. But if I plot this residual versus CPU time, the actual computing time, now we see the difference. So this blue curve, solid curve, is the split phase approach, 3rd order, and this is the flux correction approach. So one numerical flux, and this is just not. I'm using the raw flux, but it's not just the flux computation, but it includes the reconstruction to the phase. So as expected, this flux correction scheme is cheaper. And same thing for the 2nd order scheme. This red solid is a split phase 2nd order scheme, and all others are here. It's much faster than this split phase scheme. So that's what we wanted to see. But also I compared the gradients for the 1st order scheme. Basically on the irregular mesh, any scheme you lose order by 1 on an irregular mesh when you go take a derivative. So as expected, the gradient from the baseline scheme, which is 1st order, the gradient is 0th order. And it's not just 0th order, which means that this is the contour plot of the gradient from the baseline scheme. It's noisy. This is, I think, the finest grid. And the 2nd order scheme, all the same, but they all look the same. And these contours are much better, but they have some irregularity. 3rd order scheme, you achieve 2nd order accuracy in the gradients. And these contours are much better, much smoother than all others. And these are really nice on an irregular mesh. And the max 0.3 subsonic flow over smooth mount. This is the irregular hexa mesh again. And this was to demonstrate 3rd order accuracy on a curved boundary. And we don't need a curved mesh to achieve 3rd order accuracy, but we use a high order exact surface normal vector to apply boundary conditions. And then we have a 2nd order scheme here and the 3rd order scheme. And for this problem, baseline gives somehow 2nd order, but I'm sure if you'd be interested to do a grid refinement study to how long it's going to hold. But here's the residual versus CPU time again. Split phase approach is here for 3rd order, and then this is a new one flux correction approach. It's much cheaper. And the same story for the 2nd order scheme. This is a 2nd order split phase scheme, and all other schemes are here. It's faster. And then we tested this scheme for Mach 2.5 supersonic flow over triangular bump on an irregular hexa mesh. And we employed this R5 limiter for all schemes, using the same limiter. This limiter is designed to preserve up to 5th order accuracy. And the results are actually similar. And flux correction scheme is faster than split phase schemes, and they look like this. This is a density contour taken at z coordinate 0.85, so around here. There's a shock. This is the shock reflection here. So we see 2 discontinuities here. And all 2nd order schemes lined up. So you only see a blue curve and the red curve. The solutions are almost the same for 3rd order and 2nd order, even baseline. And then you can see that a little overshoot and undershoot here with 2nd order scheme, and a better captured peak here by 3rd order scheme, and a little better here. And again, this is a residual versus CPU time, and this is the split phase 3rd order. This is the flux correction 1-point flux 3rd order, and this is a split phase 2nd order, and again, all other flux correction scheme. So we basically consistently achieve faster convergence with single numerical flux. So we developed an economical 3rd order cell-centered method for mixed elements, and 2nd derivative free and a single numerical flux per quad phase to split or 4-phase split. And we prefer 4th split, of course. And we demonstrated accuracy and efficiency for irregular hexahedral grids. And the flux correction approach is more efficient than the flux phase split approach. So the future work, there are a bunch of future work. I'd like to investigate more on the limiters for third-order scheme and further numerical tests for practical CFD flow problems like hypersonic flows by NASA Vulcan CFD code and develop implicit gradient method for mixed element grids. We use quadratic least squares, but the stencil is huge. And we'd like to reduce it by using implicit approach. And another big future work is the extensions to fourth order accuracy for both implicit and viscous terms. This is possible, but this time we have to compute and store second derivatives. So the question is whether it is worth doing. And I think it is, but I'd like to find out. I already have fourth order viscous schemes, so I need to implement fourth order implicit schemes. Anyway, so it's good to have discussions and get feedback, or you might be taking an easier path without realizing. And always, have others check your decisions, and so have these discussions with colleagues, and have your papers reviewed. ARWA conference was really always a good place to get feedback, and I thank reviewers who accepted my abstract for this paper. But also, NIA CFD Seminar is another good place to get feedback. So I'd love to have your questions and comments. Thank you. Any questions and comments from the room or from online? Bill.
So on your, I think it was slide 30, you showed some look like L infinity residual plots, and the second order was 31. Sorry, the one on the right.
Oh, this is
second. Your baseline. Yeah. So is that maximum residual norm? So what does that mean? Is that L infinity, L2?
This is L1. L1 no, normalized by the initial, and then I took the maximum over 5 equations. So continuity, momentum, and energy.
So do you have any explanation of why one of them, I guess the third order plus flux correction, just continues to go down? I guess you didn't go down far enough to see if it leveled off.
Yeah, it
reasons why the other one's leveled off at different places like that.
Yeah, I just happened to stop that 4 orders of magnitude, and yes, it will level off at some point.
Is that limiter? What do you think it is?
That's I think a limiter, and this limiter has parameter k, like a Venn-gap limiter, and depending you can increase k to have a deeper convergence, allowing more oscillations. So it's a trade-off. So including this, I'd like to investigate more on the use of limiters on these schemes. Yes. Thank you.
Okay,
Boris.
yeah. One comment, so that like your formal on tetrahedral for gradient, I think it's similar what Neil Frink used.
Oh, yes.
Yeah, average.
Yes.
So you are saying that if we still kind of keep this phase average gradient minus cell average gradient, so I'm wondering, like, in terms of solution, so that so are you saying that if you would have difference between phase average solution and cell average solution, we will be able to get to second order accuracy without gradient?
Yeah, that's what you do in USM.
On tetrahedral for sure.
Non-tetrahedral, yes. Yeah, I think so.
Okay, that's very interesting. I'll think about it. Second comment, short comment. Computing phase center does not guarantee you that you still. So like one of the problems with just dividing in 2 triangles is that your actually underlying shape may be non-physical, let's say, so that when you divide it, it could be overlaps. Like, and even computing phase center value, like dividing in multiple triangles, that does not guarantee you. It actually reduces probability to have this overlap, but it does not guarantee that you do not have it. So it should be some additional test, basically. But maybe from your volume integrations, some of the pieces may come out negative, and then maybe this can serve as kind of indication that your underlying cell is deformed in unacceptable way.
Yeah. So
Otherwise, you will lose your accuracy. If you would keep this cell in undetected, it will affect your convergence. Because you will not have conservation. At certain point, you will have wrong residual computing. It's just additional thing, so that
I know. Yeah. First, I'd like to test it on a very, very bad irregular, very irregular to see if I have a problem.
Like, if you have two opposite faces in hexahedral element, just make sure that like average of these 4 points is on the other side of average of that 4 points, and you will get your twisted cell.
Yeah. So arithmetic average works as long as it works. But if it doesn't, for some reason, I can move it. But in that case, I have to compute these coefficients, interpolation coefficients, for that new point. And this arithmetic average was convenient because then the linear interpolation is just 1 over 4.
I'm not talking about arithmetic average over the cell. I'm talking about arithmetic average over the faces.
Yeah, I'm talking about face. Yeah, 1 over 4.
Oh, you say you can move?
Yeah, I can move. I just need to compute the linear interpolation coefficients for the new point.
But there will be not like if you think about that, you have let's say one face is completely planar, and another face is still intersected. So for this planar face, you will not have linear interpolation to move it out of the face. So that will not be a solution. It is will not be completely.
Okay, I thought about it actually. Now I remember. To try to compute linear coefficients. Yeah, it wasn't straightforward because if the quad face is non-planar, then it's a tet. So I can compute.
Yes, exactly.
But if it's a completed planar,
exactly.
Now I have to do 2D interpolation.
Exactly.
So there is a discontinuity there.
Discontinuity singularity. Let's go.
Singularity. Yeah, you have to. Yes. Yeah. I didn't like it, so I decided to do this.
Nobody likes it. It's just kind of one kind of condition to check to make the approach.
So I don't know. I mean, future direction should be this all text adapted. Then we don't have to worry about too much. But currently we use the mixed elements, and looks like grid generations. Those people are really doing good job. Generating nice mixed elements. So I don't know. It depends on what you want to do. But my ultimate goal is this all tet, and I don't want to look at the grid. So
all simplex. Right. All tens, all simplex.
Oh yeah, including pentatone.
Yeah.
Yes, I'm moving to 40. Yeah. Any other question? Any questions from online? Oh, Mohammed.
Well, I just have a quick thought about the scalability of this scheme. So you said that all you did was non-serial comparison. How scalable would it be? Because I think all these on each of these spaces is just a local computation, right?
Yeah.
So did you think about the scalability of it in a way, or how would that affect the economy?
That question should go to Jeff, but
Okay.
I don't know if Jeff is here.
It's a question. You spoke this direction, I did.
I'm very
that
sorry.
direction.
So I'm wondering about the scalability of this, since,
But it's,
yeah, I think all the computations are
oh,
local on the
Yeah, yeah.
phase. So I was just wondering how that
It
would
should-
affect
should
the
be
plans of the
Scalable as any other scalable. method.
Yeah.
There is no global computations.
yeah, the point is to keep the algorithm as close,
Yeah.
to a second order algorithm as possible.
Yeah, I
So
get that, yeah.
I don't see a big difference from second order scheme, so.
There is no expansion of the fellow, so that it's the same, just the nearest neighbor computation, so. Should
Yeah.
be as scalable as anything.
Mhm. Yeah. Any other questions? Bill?
So you keep on talking about gradients here. I think you mentioned you get them from least squares,
Oh, least squares, yes, quadratic groups.
quadratic least squares.
Yeah, so gradients at the node and using the solutions stored at cells around this node. And we go neighbors and their neighbors. So it's a huge extensive, like
So
200.
that would require additional communication, so that if you go to neighbors of neighbors,
Yeah,
that would require additional communication.
yeah.
So that would affect scalability.
If you do your implicit gradients, then
But I think you're doing it like in two passes, right? So that
Yeah,
you basically, you still use the same
yeah.
communication stencil, you just compute it in two passes.
And we store them at nodes.
Yeah.
And
So it's little bit reduced scalability because it would require two communications instead of one, but nothing kind of
but yeah,
prohibitive.
but the same for second order scheme, actually. Even for second order schemes, we have huge stencil. So
But states it's only neighbors.
no. Neighbors,
Okay,
and then
I don't know about your scheme, but like, say,
yeah, if you use neighbors, then there is a difference, but
I mean nodal neighbors, so that you use nodal neighbors.
but cells around the node
Right. So you,
and their neighbors. Neighbor cells. So
okay, that's for you because you need to compute gradient with nodes.
yeah.
Right, so that if you would not need to compute gradient with
Yeah, for
nodes.
second
it would
order,
just immediate-
we could do with just neighbors, but we found including more neighbors can be made.
It's not neighbor of the cell. You still include nodal neighbors, so that, but it's just neighbors. It's not neighbors of neighbors. It's not, you don't go beyond neighboring cell. Okay, I can
We
do
go
it
beyond.
so that, yeah, we can. There is little bit less scalability if you go to neighbors of neighbors.
Yeah, if you go. Any other questions, comments? Bill?
Does anybody online? Is there any online questions first?
No questions from online?
Okay.
No, no.
So, I know you're saying ultimately you'd like to get back to tetrahedron.
Mm,
If we happen to borrow Boris's grid generation person and they make oddball tetrahedral, pancake cells or something like that, the face normals won't span the three-dimensional space very well. If you form the dual mesh, then you get normals that might span three-dimensional space better. And you might be able to use this technique on a dual mesh and get more of a multi-dimensional flavor to your flux propagation.
It's like nodes and the cells.
yeah, no center and you,
But this would scale to the shape of whatever that dual volume was. There's no constraint on the shape of the volume.
a true polyhedral method, you're saying.
Yeah, every
The-
facet could have a different number of points defining it, and yeah, there could, because it's just face, well, as long as you computed the weights.
My regeneration person can generate the dual cells as bad as. So it's maybe less probability, but definitely not certain.
yeah. But it's interesting to think think about extending this method to node-centered scheme because it's for Hiro. But I think it's possible. But then you need to compute and store gradients at nodes. Now, apply that to node-centered. Now you need gradients at
the nodes will have different nodes.
different. Yeah.
So the nodes now going.
It's forming the.
It's actually going to be cell-centered. Now nodes going to be cell-centered.
Yeah. Yes. So it's a little bit different, but
the midpoint of each edge.
And now that you lose this advantage that now that the number of nodes and regular grid is much smaller than the number of cells. In this case, it is opposite.
Yeah. So. Yeah. But the advantage, I think, I have to demonstrate this, but I think fourth order accuracy is possible with this approach. That's one unique advantage. For node center, we have third order H-based scheme, but that's third order maximum. Boris, what do you think? Do you think you can get a fourth order accuracy for H-based scheme?
The real question, do I want
Yeah.
I don't know what is it.
Yeah.
That's the real.
So do Rowe's arguments for his third order hold any longer? Remember when he came up with the active flux scheme, he made a whole argument for why third order was the sweet spot there.
Yeah.
I think the main advantage of third order that it can be basically achieved on the same stencil as second order, so that you effectively get
No curve,
higher order for free.
no curve meshes.
No curve meshes, right? So that's if you need like the fact that you need to compute second derivative for me, make me
Not very happy.
stop. Yeah, okay, but at least I need to have really strong motivation to do it, so that I need to want to do something that I cannot do today in a different way. So if I have this, if this is the only way to go, we need to go. But
Maybe somebody's put weight on your controller. Put easy around, man. Come on.
I don't think that easy route is bad. So that I think it's maybe problematic when we make ourselves to go difficult route when we can achieve the same thing by easy route.
Of course.
In the context of Vulcan, let's say you have multiple species, and some of the species may be important at trace level because maybe they're a catalyst for a reaction or an ignition or something like that. Other species may not be so critical at a trace level. They may just be kind of the waste products. With your scheme, could part of the scheme be for certain governing equation moment or mass equations, rather be second order, others be third? Can you choose?
That's interesting.
It's like computing all the gradients to neighbors of neighbors for all the species, for example. Could you selectively choose certain equations to be third order or second order?
Yeah, I think that's a very interesting question. It's like a limiter, right? I mean, in the limiter, you switch from between second order and first order.
But if you knew not to, like, if you knew some species, for example, I don't need very accurately, so I could just not even bother to compute the gradients, sort of store the gradients, or assume they're just linear or something.
Yeah. I've never thought about it, but I think it's an interesting question.
You will lose global accuracy on everything, right? So if you have any element that is first order, every element is first order. It's non-linear.
I mean, just for one mass equation.
You still like it may help you in a short term, like while you converge it, but I mean. How much it will affect the global accuracy? Who knows that? And that's also typically a question: is second order necessarily less accurate than fourth order? So that's kind of more deep question, but you lose kind of at least formal order properties if even one element is not that order.
Yeah, unless that component is simply a constant. Any other questions online? No questions? Okay.
Tell everybody online that the pastry was very good.
What?
Pastry was very good. They missed on the
Food is very good. Please come again. We will have another seminar in February 18th, and then March, 2 seminars in March. So please come. Okay, thank you, everybody. I think we can finish here.